The last time we drew several Lewis structures, methane, ethane, ethene, and ethine. Alkanes, alkenes, and alkynes were the functional groups we covered. It's now time to draw a few more Lewis structures, talk about a few more functional groups. So I think it's probably useful that we remind you of some of the Lewis structure rules. You first find the total number of electrons in a molecule. That's by adding up the number of valence electrons. And remember, the group number tells you the number of valence electrons available. Carbon is in group 4, he has 4 valence electrons. Oxygen is in group 6, he has 6 valence electrons, etc. So remember that if a thing is charged with a positive or a negative, you have to change the electron count based on that. Negative means it gained, positive means it lost. Yep. So when we're drawing all these carbon-containing structures, remember carbon is a neutral atom. It's not super electronegative, it's not very electropositive, it's in the middle. So it can make bonds to lots of different atoms. Additionally, carbon is in group 4, which means it needs 4 electrons to make an octet. So carbon likes to make a lot of bonds, as in 4 of them. Carbon always needs to make 4 bonds. So carbon is often the central atom in what we're drawing in this class. And then all the other stuff is around the outside connected to carbon. If you have lots of things, the rules from general chemistry said, put the least electronegative atom in the center and the electronegative stuff goes around the outside. Well, when carbon and hydrogen are connected, remember carbon goes in the middle and hydrogen around the outside, which is a little bit against that rule right there. So we'll see some things called condensed structural formulas. I'll show you what those are momentarily. Those tell you hints about how the molecule is connected. You'll see. So remember that every time you draw a line connecting 2 atoms, there are 2 electrons in that line. We will make double and triple bonds as well as single bonds when we need to. We will try to fulfill everyone's octet, but there are some exceptions to the octet rule. Who are some of the exceptions? Well, we've already seen that hydrogen is an exception. Hydrogen only wants 2 electrons, not 8. We have seen from general chemistry that boron and aluminum are exceptions to the octet rule. We've seen that things like sulfur and phosphorus are exceptions or can be exceptions to the octet rule. So boron, carbon, hydrogen, boron, and aluminum, they want less than an octet, or they have no formal charge when they have less than 8 electrons. Sulfur and phosphorus and other things in the 3rd period and beyond can have more than 8 electrons and still be neutral, still not have a formal charge. Speaking of formal charges, we're going to do a lot of formal charge assigning in this class. So here's the formula that we will use to assign formal charges. So be familiar with it. Well, in order to consider that, you have to know how many bonds things typically make. What kind of things, remember we're talking about the top right corner only really, what kind of things make 1 bond out of the top right corner of the periodic table? Well, the things that we come across that typically make 1 bond are hydrogen. Yes, it's not in the top right corner, it's an outlier always, but hydrogen and the halogens. Remember, those guys are called halogens. All of these are halogens. So the halogens are all in the 7th group of the periodic table. So they need 1 electron to make 8. So they make 1 bond. The difference between the hydrogen and the halogens is the halogens all have 3 lone pairs in order to give them a full octet. Hydrogen, not so much. From that top corner, what likes to make 2 bonds, aka what is 2 electrons away from an octet? Things in group 6. That's oxygen. So oxygen likes to make 2 bonds. When oxygen makes 2 bonds, he must also have 2 lone pairs. That oxygen can make 2 bonds that are 2 single bonds. It could also make 2 bonds as in a double bond, and it still must have 2 lone pairs when it's making a double bond. How it bonds, whether it's single or double, doesn't matter, but oxygen prefers to have 2 bonds. Can it make more than 2? Yes, but it's going to get a formal charge that way. Can it make less than 2? Yes, but it's going to get a formal charge that way. Okay, from that same top quadrant, things in period 5, no, things in group 5 have to have 3 electrons to make an octet, so they like to make 3 bonds. That's nitrogen. When nitrogen makes 3 bonds, he has a lone pair as well to give him an octet. Just like before, nitrogen can make 3 single bonds. Nitrogen can make a double and a single, still have a lone pair. Nitrogen can make a triple bond and still have a lone pair. We don't have to delineate this for all of these examples. These are just possibilities of making 3 bonds, but you'll get the hang of it. And finally, who makes 4 bonds? Our favorite, carbon. That can be 4 singles, 2 doubles, a single, 2 singles, and a double, etc., etc. You got this. So I said oxygen can make more than 2 bonds, but it would get a formal charge. It can make less than 2 bonds, but it would get a formal charge. In fact, nitrogen can make more than 3 bonds, it would get a formal charge. It can make less than 3 bonds, it would get a formal charge. Really doesn't make less than 2, but we'll talk. Carbon, though, carbon cannot ever make 5 bonds. Carbon cannot ever make 5 bonds. In fact, oxygen and nitrogen also cannot make 5 bonds or have 10 electrons around it. These guys are in the second row of the periodic table. You cannot exceed the octet for any of these, oxygen, nitrogen, or carbon. Carbon can make less than 3 bonds, but it would get a formal charge. We will talk at length about that later. Well, let's move on to actually drawing some Lewis structures. The first thing it said to do was total up the number of electrons that you have. That means you need to know valence electrons. Carbon is in group 4, so he's got 4 valence. Group 4, he's got 4 valence. Oxygen is in group 6, he's got 6 valence. Hydrogen is in group 1, so he's got 1 valence, but there are 6 of them in this molecule in total. So we're going to add and get 6 plus 6 plus 4 plus 4, 20 electrons in this molecule overall. So this is a condensed structural formula. That means it's hinting at how the molecule is connected. So this carbon, this first carbon, let me clear up some space here. So this first carbon is connected to the things that follow it. C with 3 H's. This carbon, though, needs to make 4 bonds in order to be satisfied, and we're aiming at satisfying the octet rule, but occasionally have to break those rules. This carbon is also connected to the next carbon in the line, and that carbon is connected to the 2 hydrogens that follow, but he has another vacancy in order to make 4 bonds also. So this carbon is connected to the next thing in the line, which is oxygen, and that oxygen is connected to the hydrogen that comes next. So that's sort of a basic foundation that my condensed structural formula helped me put together. But is this a complete Lewis structure? No. For 1, 2, 4, 6, 8, 10, 12, 14, 16 electrons have been used, and I've got 20. Where are those remaining 4 electrons? Obviously, they're lone pairs on the oxygen, because if you go to 1 slide back, carbon likes to make 4 bonds. Both carbons are now making 4 bonds. Oxygen likes to make 2, and oxygen was making 2. But when oxygen makes 2, he needs 2 lone pairs to fulfill his octet. Does the typical bond numbers need to be something you memorize? No. The way we got there in the first place was knowing how many electrons were needed to get to 8. That's what you're asking yourself again and again and again when drawing Lewis structures. So this molecule is CH3CH2OH. All right, so I said we are going to draw more Lewis structures today and learn more functional groups. It's time to talk about the functional group or groups in this molecule. This bit of the molecule makes this thing an alcohol. And some students may say, well, there's stuff over here that's carbon and hydrogen only single bonds, so you may call that bit an alkane. So The reality is, as organic chemists, we see so many carbon and hydrogen all single bond type things that even though I led you to believe an alkane is a functional group, it really officially is. This molecule would generally be referred to as an alcohol alone because the alkane part is not as flashy, not as important. As we get into more reactions, you'll see it doesn't do as many reactions. So I know it's only the second day, but I'm just trying to plant seeds for future knowledge. You don't have to label this as an alkane group, but you do need to label this as an alcohol group. So let's talk about alcohols in general. What are alcohols? An alcohol is an R, OH. In chemistry, in organic chemistry, an R means any carbon group. So the carbon group over here is an alkane officially. It's an S because it's 2 carbons. It's an ethane-ish, we'll explain. So this R group could be lots of things. If it's just plain hydrogen, that's not an alcohol, that's water. But it could be an alkane group over here, or maybe even an alkene group. We'll see a lot of things. A carbon group connected to an OH is an alcohol. So we're reminding you of all the Lewis structure rules from Gen Chem stuff and starting to build on why it matters for organic chemists. Well, one of the things that organic chemists do is we don't always draw a full, complete Lewis structure like this. And you say, what? Yeah, we take shortcuts and we draw the molecule like this. What? This OH bit is OH, but because we love carbon so much as organic chemists, we say, I don't want to always draw out every carbon and every hydrogen in a molecule. So I'm going to say this little kink at the top of this apex, top of this point, is a carbon. And as well, this carbon, this end of the line, is going to be that carbon. So we take advantage of, organic is all about carbon, and we assume that carbons exist at the vertex and endpoints of lines. Yeah, we do. Additionally, because we know carbon needs to make 4 bonds in order to be satisfied, when we assume that this is a carbon, you assume enough hydrogens are there in order to make it have 4 bonds. So the endpoint of a line is going to have 3 hydrogens connected to it. This point, because it's got oxygen and carbon also connected, has 2 hydrogens. So I realize this may feel like we're going over a lot right now, but these guys are called skeletal structures. It would help if I spell it correctly. These guys are called skeletal structures, and we will draw tons and tons and tons of skeletal structures. So I think it's good practice that as you're drawing, as you're taking these condensed structural formulas to come up with a total Lewis structure, I think it's helpful to then convert that Lewis structure to a skeletal structure, because that's how we'll see molecules most of the time. I have one more thing to say about this molecule before we move on to the IRs. This molecule has 2 carbons, so his root name would be S. It does not have any double bonds, so it's an ane, A-N, or an, but it does have an alcohol. And so naming alcohols, we will go over more rules later, but naming alcohols, they become an OL on the end instead of an E. So this is not an ethane, because ethane would have 6 hydrogens all connected to carbon. This is ethanol. S, 2 carbons, AN, no double bonds, no triple bonds, all, there's an OH connected to the carbon. So this is ethanol. Let's look at the IR of ethanol. This is it. So remember, the right-hand area over here is the fingerprint region. I nabbed this off the internet, and they did label a couple of peaks in the fingerprint region, and we will talk about what those labels should be, but today is not the day for that, so let's ignore that whole side over there. We said ethanol has carbons and hydrogens and only single bonds. We called this functional group an alkane if we were naming it a functional group. And remember, this area, this set of peaks, is the alkane stretch area. It's officially the sp3CHs that are stretching in ethanol. But look, there's something else that does some stretching in ethanol. It's an OH bond. That OH must be what's responsible for this big, wide, gnarly stretch over there. We'll talk about the regions you need to know in IR stretches later, but really it's kind of recognizing the pictures and what bonds are what stretch areas. Yeah? Let's draw another Lewis structure. This middle guy. If we add up all the valence electrons, we get 4 plus 4 plus 6 plus 1 times 3 plus 1 times 3. Hopefully you can add that. 20. We got 20 electrons in this thing also. So my carbon is connected to 3 hydrogens. Carbon connected to 3 hydrogens. That carbon is connected to the oxygen as well because carbon needs to make 4 bonds. Oxygen. Oxygen has no H's connected, so that oxygen is connected to the carbon that comes next, and that carbon has 3 hydrogens on it. This is my skeletal structure, my loose framework for what my Lewis structure looks like, but it's not complete because if you count 2, 4, 6, 8, 10, 12, 14, 16, I've used 16 electrons. Oxygen needs 2 lone pairs in order to use my complete 20. Excuse me. In order to use my complete 20. Yes, I could edit that out, but I'm not going to. So remember, oxygen makes 2 bonds, has 2 lone pairs, carbon makes 4 bonds. Check, check, check. Everybody's octet is satisfied. This is a legit Lewis structure. So if you noticed this and this, if you wrote C2H6O, that fits both of these Lewis structures, but they are very different molecules. This first one was an alcohol functional group, remember. This second one is not an alcohol. There is not an OH connected to a carbon group. We have an oxygen with carbon groups on ether side of it. So this is called an ether functional group. This molecule overall is an ether. Ethers officially have 2 lone pairs and 2 carbon groups always. What would the skeletal structure of this ether look like? An oxygen with a single line on either side, because the end point of this line is an implied CH3, and the end point of that line is an implied CH3. I didn't point it out on the last example, but in skeletal structures, it's common to leave out lone pairs. You have to assume the lone pairs are there in order to make a neutral molecule. So remember, oxygen, 2 bonds, 2 lone pairs. You'll get it. Ready to see an IR of an ether? Here it is. This is officially dimethyl ether. That's the name of that last ether, but we're not going to worry about naming it now. What are these sets of peaks? That would be sp3ch stretch. We had 2 CH3s. Those are sp3 carbons. They have carbon, hydrogen, sp3 stretches. This is a little baby peak where it's officially in the functional group region. Meh, we don't care. Other than that, there's nothing in the functional group region to label. All this stuff is in the fingerprint region. So that's because a carbon oxygen single bond stretch does show up in the fingerprint region. So we really ignore the fingerprint region almost all the time. But an ether compound has nothing to identify in the functional group region besides alkane stretches, those sp3ch stretches. So we look into the fingerprint to identify a C single bond O stretch for an ether. If you look back at that alcohol IR, it also has a C single bond O stretch. That's what's labeled in the fingerprint region, but that's neither here nor there. Moving along. Our last molecule over here, if we total up the number of electrons that we have to work with, we get 4, 4, 6, plus 4 more. We have 18 this time. 18 electrons to work with. So if I start building my Lewis structure, carbon is connected to 3 hydrogens. That carbon is connected to 1 more hydrogen. That carbon is also connected to oxygen. So if I counted here, 2, 4, 6, 8, 10, 12 electrons have been used. But I have a problem. Carbon likes to make 4 bonds. The carbon on the left is making 4. The carbon on the right is only making 3. Oxygen likes to make 2 bonds, and the oxygen is only making 1. Put a double bond between that carbon and oxygen. That gives everybody the number of bonds that they like to make. There are times when we will not use this as our crutch for building Lewis structures, but it's just the beginning. So this is my loose framework for what this molecule should be, but remember, oxygen needs 2 lone pairs when he's making 2 bonds. 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. This is my Lewis structure. Isn't it great? This Lewis structure has a carbon doubly bonded to an oxygen with a hydrogen on one side and a carbon group on the other side. That functional group is an aldehyde. Aldehydes must have hydrogen on one side of your COO. Must. What would the skeletal structure of this guy look like? It's officially that, but often to be a little helpful, a little more obvious, we draw the hydrogen on the other side over here. It's absolutely not required, and an official skeletal structure doesn't have it because it can be assumed. So this carbon does have a hydrogen in order to make a 4th bond, but it's often drawn with that 4th hydrogen, with that hydrogen explicitly shown. This one over here must have 3 to make it have a full octet. So you can draw this top skeletal structure, the bottom skeletal structure. We will draw both and see both pretty frequently. So here is the IR of acetaldehyde. I know we didn't name that molecule, but it's the one we just saw. So acetaldehyde has, as expected, just to the right of 3000, a grouping of peaks. And that grouping of peaks is sp3, CH stretches. Aldehydes also have a unique stretch that shows up to the left of those. That's this. It's often 2 single fingers, actually. This one shows a couple more peaks than that. But those 2 fingers are the CH of an aldehyde stretch. Other functional groups do not show this. Aldehydes have a CH of an aldehyde stretch just to the left of our normal sp3 CH stretches. And the final stretch that we see in an aldehyde spectrum is this one. This thing is out there in the functional group region, so we need to label it. That is known as the C double bond O stretch. Anything and everything, any and every functional group that has a C double bond O will have a C double bond O stretch in that region. Awesome. Okay, so we've drawn today an alcohol, an ether, and an aldehyde. Let's do more. All right, hopefully you've gotten good at totaling up electrons. 4 plus 5 plus 5 more from hydrogens. This one has 14. CH3 is how I start. It's how so many organic molecules start. Connected to a nitrogen. Nitrogen has 2 hydrogens. And nitrogen with 3 bonds has 1 lone pair. Done. I should have mentioned prior to now, but I forgot. It does not matter which direction you point these atoms. If you drew this same molecule this way, It doesn't matter. It's the exact same molecule. It's just pointed different directions. You could have the nitrogen pointed down. You could have the hydrogens on the nitrogen pointed different directions. It doesn't matter. Remember, Lewis structures just give you connectivity, but we have to think three-dimensionally to really see what this molecule looks like. And three-dimensionally, we don't have 90-degree bond angles, even though I've drawn them as their 90-degree bond angles. So once you consider three dimensions, it doesn't matter. This molecule is that molecule. They are identical. And the same thing with all the ones we've drawn previously in this video. Okay, so I've got a carbon connected to a nitrogen. It's officially an NH2. So that is an amine, A-M-I-N-E, amine. If you look through your textbook specifies primary amine, secondary amine, tertiary amine. We're not worried about that right now. We want to call this thing an amine. We're also going to call things that have 2 carbon groups and 1 hydrogen an amine. And we're going to call things that have 3 carbon groups an amine. So a nitrogen with a lone pair connected to any combination of carbons and hydrogens, that's an amine to us. And there's something that I want you to know about amines. Amines are good bases. Amines are good bases. That means it's a good acceptor of a proton. Oh man, acids and bases, we're going to talk so much about them, but we're still building our Lewis structure foundation right now. Amines are good bases. When I ask you later, there's one thing you know about amines, and it's that they are, you say, good bases. So we'll draw the little skeletal structure of this guy. That's nitrogen with 2 hydrogens and a stick coming off. That is methylamine officially. Methylamine has a kind of messy IR. So we're going to look at the IR of propylamine. Hope you're okay with that. As we learn more and more functional groups, I think you can probably realize that the IRs get a little bit more sophisticated, a little bit more complicated with how many things you need to identify. But there's one thing that's almost always in our IR, and that's this. To the right of 3000, that's an SP3CH stretch. Also, in our functional group region, we've got this peak, this set of peaks. That's called an NH stretch. How do you tell the difference between an OH stretch and an NH stretch? An OH stretch comes in the same region over here, if you remember back to our alcohol. But an OH stretch had a smooth bottom. It had a very smooth transition down here. An NH often has a couple of bumps, a couple of fingers is what I refer to them as always. So if you have a smooth transition, probably an OH. If you have fingers pointing, probably an NH. You'll also be able to tell that simply by knowing the molecular formula of what your molecule is, but we'll get to that. There's another thing here outside of the fingerprint region in the functional group region. That's an NH bend, but we don't really talk a lot about bends in this class. We talk more about stretches. Stretch, stretch. I will not require you to label this as an NH bend, but if you do some Googling, some internet searching stuff, you'll probably see that that's labeled as an NH bend. Okay, moving along. 1 plus 5 plus 6 times 3. I've got 24 electrons in this one. 24 electrons. This Lewis structure is not a typical condensed structural formula. For one, do you see any carbons in there at all? No. This one is what's known as an oxoacid. Maybe you looked at that Lewis structure, HNO3, and said, oh, I know that. I know that. What is that? I know that. Nitric acid. So nitric acid has nitrogen as the central atom, oxygen surrounding the nitrogen. And if you look back at your rules of Lewis structures, an oxoacid, the hydrogen that's involved, or hydrogens that are involved in oxoacids, are connected to oxygen, not the central atom. The hydrogen is not connected to the nitrogen here. As it turns out, this is also an oxoacid. His name is sulfuric acid, but you knew that. So we're going to have sulfur with 4 oxygens connected. And where are those hydrogens connected? To the oxygen. Sulfur with 4 oxygens connected. And the hydrogens connected to the oxygen. Does it matter which of those oxygens? Not at all. Remember, we're drawing it as a 90-degree kind of structure, but three-dimensionally, it doesn't matter. So these are my basic framework structures of these 2 molecules. I didn't even tell you yet, but sulfuric acid has 32 electrons, if you can read that back behind my drawing. So let's finish off both of these Lewis structures. Nitric acid has 24. We have used 2, 4, 6, 8, only 8. Nitrogen does not have an octet. So according to my bond counting rules, he likes to make 3 bonds. He's making 3 bonds. So I don't immediately want to make more bonds. But my oxygens are a bit dissatisfied. So how do I make everyone satisfied? I'm going to start by putting 2 lone pairs on this oxygen, because I know that oxygen with 2 bonds wants 2 lone pairs. Check, check, that one's done. But I cannot turn both of those into double bonds. It even hurts me to draw it. I cannot turn both of those into double bonds, because that makes nitrogen have not 8, but 2, 4, 6, 8, 10 electrons. That exceeds nitrogen's octet, and that is not acceptable. He's too small for that. So we cannot draw 2 double bonds. So if I tried to leave nitrogen satisfied with having only 3 bonds, I would need a lot of lone pairs to fill up everybody's octet. So here I go, filling up all the octets of everybody. That makes me use 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Uh-oh. That's more electrons than I really have to work with. I've used 26, but I only have 24 available to me. When that's the case, you have to take off a lone pair, -2, -4, take off another lone pair, make a double bond between the thing that you just erased electrons from. So this is the Lewis structure of nitric acid. That's almost complete. What's missing from it? When something makes a different number of bonds than is typical, we have to account for formal charges. So if we look at this oxygen, he's making 2 bonds, that's what he likes. He's a neutral, 0 formal charge. This guy, he's making 2 bonds. That's what oxygen typically makes. He's a neutral, 0 formal charge. This guy, not so much. This guy is making 1 bond. That's fewer than he likes. So then we go to our formal charge equation that we saw previously. The equation says, take the group number, oxygen is in group 6, and subtract the number of lone pair electrons, that's 1, 2, 3, 4, 5, 6 in this guy, in parentheses, add together, the number of lone pair electrons plus the number of bonds that are being made, and subtract that total from the group number. So I've got a 6 minus a 7, that's a -1. What that means is this oxygen has a -1 formal charge. Was that good enough? Let's see that again. Nitrogen is making more bonds than it typically likes to make. So we take its group number, which is number 5, and subtract from it the sum of the number of lone pair electrons, that's none for this nitrogen, plus the number of bonds it's making. So 5 minus 4, that's a +1. This nitrogen is a +1 formal charge. Whew, that's familiar. I remember that a little bit. Yeah, we're going to do that a lot. So you should practice a lot and get really good at it. But I trust you will. So that's nitric acid. Well, let's finish sulfuric acid over here as well. Sulfuric acid, oxygen likes to make 2 bonds and have 2 lone pairs, so I could automatically put 2 lone pairs on the oxygens that have hydrogens connected. Sulfur is in group 6. That means it's similar to oxygen in some ways, but sulfur is also in period 3. So what that really means is sulfur can exceed its octet. So if I satisfy these oxygens by making 2 bonds, that gives sulfur 2, 4, 6, 8, 10, 12 electrons. But sulfur is a big guy, as in has a large radius. He has the 3rd shell of electrons available to him. So it is perfectly acceptable for sulfur to be drawn with more than 8 electrons around him. So if I fill in my lone pairs on oxygen and I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Check, check. This is the Lewis structure of sulfuric acid. Is there anyone that's making different from their typical bond numbers? All the oxygens and hydrogens are satisfied, but let's double check the sulfur since this is the first time we've seen sulfur. Sulfur is in group 6. How many lone pairs on this sulfur? None. How many bonds is this sulfur making? 6. So when you do that math, that sulfur actually has a 0 formal charge, which is great. The best Lewis structures have the fewest number of formal charges, but sometimes you can't avoid them, like over here in nitric acid. Remember why we couldn't make a double bond here? Because that would explode nitrogen's octet, and that is not okay. But you can do it with sulfur because he's a big guy in the 3rd period. Okay, that's nitric acid and sulfuric acid. We will see those a lot throughout this course, so be familiar with their Lewis structures. We don't need to worry about new functional groups. Those are specific molecules, nitric acid and sulfuric acid. Moving on to the next Lewis structure. 4 electrons in carbon, plus 6 electrons in oxygen, plus 1 for every hydrogen, plus 1 for sodium. We get a total of 14 electrons in this thing. CH3, oxygen. And then you say, sodium? And I say, Sodium is a hater. Sodium does not share. Sodium is a metal. Metals do not make covalent bonds. Metals make ionic bonds. Ionic bonds tell you that electrons have been completely transferred. So the electron that really started on a sodium gets transferred to this other molecule. So this is oxygen accepting that electron from sodium. So sodium doesn't really have it anymore because it transferred it to oxygen. It transferred it to the more electronegative atom. So this molecule has some covalent bonds. These 4 things are covalent bonds, but it also has an ionic bond between the sodium and the oxygen. Ionic bonds have charges. Sodium has one fewer electron than it began with. It's a positive. We can do that with our formal charge counting as well. Sodium is in group 1. How many lone pairs does it have? None. How many bonds is it making? 0. So sodium is a +1 because our formal charge formula tells us so. Carbon is making 4 bonds, so he's neutral. Oxygen's only making 1, not neutral. Oxygen is in group 6. This oxygen has 6 lone pair electrons, and it's making 1 bond. So 6 minus 7, -1. Oxygen has a -1 formal charge. This oxygen and sodium are not sharing electrons. They are completely transferred. So that means this thing is ionic. And yesterday we said ionic things are soluble in water. So this molecule would dissociate in water into a sodium cation and an OCH3, a CH3O minus, that's how I want to say that, a CH3O minus anion. There is another thing that I want to say about this. It's not exactly a new functional group, but it kind of is. CH3OH, what functional group does that have? That's an alcohol. What's the difference between this orangish molecule and the blue one? There's an H missing. When a hydrogen is lost, that means this thing acted as an acid, and this thing is a conjugate base of that acid. We say it's the conjugate base of an alcohol. So it's not really a new functional group to learn necessarily. It's a conjugate of a functional group we already know. If you do refer to it as a separate functional group, it's called an alkoxide. The oxide, IDE, ide, chlorine becomes chloride when it gets an extra electron and becomes negative. Oxygen gets a negative, becomes an oxide. And the alk tells you there's some carbons connected to that oxide, alkoxide. Cool. When we draw skeletal structures of ionic things, we do sometimes draw them connected looking like that, but you must always know that even when they look connected, this oxygen is ionic. This molecule is ionic. This oxygen is not directly connected to the sodium. They're associated together like positive attracts a negative, but they're not sharing electrons. So we often do draw them completely separated like this with their charges shown, but it's totally acceptable for us to draw them together like this top example, but you assume that those charges are there. Yeah? Okay, cool. So if we do this next one, we're coming to a close here. Carbon has 4 electrons, nitrogen has 5 electrons, chlorine has 7 electrons, and there are 6 from hydrogens. That gives me 22 total electrons here. Carbon has 3 hydrogens. Nitrogen comes next, and apparently the nitrogen has 3 hydrogens. And then where the heck does chlorine plug in? It doesn't. There's nowhere for chlorine to make a bond to share with the carbon or the nitrogen, because the carbon is full, the nitrogen is full. Both the carbon and the nitrogen already have an octet. So the chlorine must be not bonded to those, not covalently bonded to those. So if I count my electrons, 2, 4, 6, 8, 10, 12, 14 have been used in bonds, but I've got 22. Where are all of those electrons? They're lone pairs around the chlorine. Now I've used the appropriate 22 electrons. So this is my Lewis structure, except I noticed that some of these things are making more and less bonds than they're used to. Chlorine usually likes to make 1 bond, but he's making no bonds. He's in group 7. Right here, he's got 8 lone pair electrons. He's making no bonds. 7 minus 8, -1. This chlorine gets a negative charge. Carbon makes 4, he's making 4. Nitrogen likes to make 3, he's making 4. Nitrogen's in group 5, minus no lone pairs, plus 4 bonds in this molecule, plus 1. My nitrogen is positive. That's great news because overall, my Lewis structure is neutral. You don't see a charge up here in my Lewis structure overall. So I have to have charges that complement each other to cancel out to get me a 0 charge overall. This molecule is an ionic molecule. I've got a cation, that's this NH3 plus kind of thing, and an anion, that's my chloride. Similar to the last one, this is not really a new functional group per se. It's building off of another functional group we've already talked about. This is a functional group we've already talked about. It's an amine, A-M-I-N-E, amine. This amine can gain a hydrogen at this spot right here, gain a hydrogen to become this. So amines, there's one thing you know about them, and it's that they are bases. So this molecule on the left is the conjugate acid of that amine because it has an extra hydrogen connected to it. So the conjugate acid of an amine is sometimes referred to as its own functional group thing and sometimes referred to as the conjugate acid of an amine. But if you refer to it as its own functional group, you would call it an ammonium ion. That tells you it's an it's going to have a positive charge, and it's an ammonia-looking thing that has that positive charge. It's an amine-looking thing that has that positive charge. If I draw the skeletal structure of this guy, it can be drawn this way, where the NH3 and Cl look like they're connected, as in they're squished together, but we often draw it this way, with the positive and the negative explicitly shown on my two ionic pieces. So I've drawn a ton of Lewis structures for you. It's time for you to draw some of your own Lewis structures. You should practice these on your own. We will probably discuss them a bit later. But yeah, definitely, you should practice them. Each of them has at least one non-zero formal charge. Make sure you remember and associate that, because formal charges are important. Why are they important? Well, we will graduate to drawing lots of skeletal structures like we've been talking about a little bit here. This skeletal structure with a negative charge just floating nearby this single carbon, that negative charge makes me know how many hydrogens to connect to that carbon. This one is a CH3 with a plus, but let's draw something a little bit different. This positive charge floating next to that carbon makes me know how many hydrogens are connected to that carbon. This endpoint has three hydrogens. This one has 2 hydrogens. This one has 2 hydrogens. This one has 3 hydrogens. Because all of those are neutral, they need to make 4 bonds in order to make them neutral. But this carbon that has the positive, carbon is in group 4, and in order to have a positive charge, it means that it needs to have 3 bonds, or what that generally means is it's got 0 lone pairs and 3 bonds in order to make it have a positive charge. So this carbon with a plus actually only has 1 hydrogen connected to it. That formal charge indicates that there's only 1 hydrogen connected. But this middle example, the ending carbon has 3 hydrogens, but this right terminal carbon has 2 hydrogens. The reason I know that is because this is the molecule that I just drew. But if I did my formal charge formula, 4 is carbon's group number. I need to have a -1 formal charge. Carbon can never make 5 bonds, so it must be making 3 bonds and have 2 electrons as a lone pair. So that carbon with a minus is a carbon with 3 bonds and a lone pair. Does this carbon with a plus have a lone pair? Absolutely not, never ever. But carbon with a minus has a lone pair. So formal charges help you know how many hydrogens are there and how many lone pairs are there. That's 2 examples with carbon. This nitrogen does not have a formal charge, but it does have a lone pair because nitrogen that's neutral has a lone pair. So formal charges are important. You should get used to them, get good at them. It'll be fun.